Welcome to a lesson with Dr. Powell. Let's take a look at this idea of taking a derivative without actually solving for y. That's called implicit differentiation. We have an equation and we take a derivative of both sides. I'm going to do it strategically. Suppose that we have something like x times y plus y squared. Okay, so and suppose this is equal to 2, okay? Now, let's take a derivative of both sides of this equation with respect to x, but we're going to do this strategically. Let's use a boxing rule where we think of, and we can use repeated boxes. In other words, our one box will be this one. And the other box will actually be this one, but notice how it repeats in the expression. So using that idea, we proceed as follows. So it's okay to have a repeating box. That's just fine. And taking a derivative this way is actually extremely beneficial, as we'll see when we're trying to solve for dy dx. On the right, the derivative is just 0. Now, if we take the derivative thinking of x as being the variable and everything else is constant, so think of the y as being like a 4, like a 4x, the derivative would just be 4. Well, instead of 4, you have y. So the derivative here would just be y, and the derivative of y squared as a constant would be 0. Over here, if for the repeated y box, here and here, we think of anything else as being constant. So we take a derivative. In this case, it's just x times, so x is a constant, times y. Now, what would that be? Now, it's like we have the derivative of something when we're plugging in y into it. Now, y we're going to think of as being a function of x, and we have an x as a constant for a minute. So now composition always turns into multiplication. Derivative of y is dy dx. The derivative of something is just, well, just a variable. With respect to that variable is just 1. Like the derivative of x is just 1. We're going to use that basic idea, except in this case, x is a constant, but it's just going to remain as a constant multiplier. So the derivative of this piece over here is simply going to be x dy dx. Now, okay, now let's go to this piece right here. This is a lot like, again, this is the same basic idea. We have a function with y plugged in, so it's a composition. All right, this turns into multiplication. We get y prime or dy dx, and this part is just 2y times dy dx. And maybe we can write that down and in that notation. Okay, so we get that. So that's what this part is. So we just put that in right here, plus 2y dy dx. Now, why was it good to use this boxing technique this way? Because here we can factor out a dy over dx. And we have an x plus 2y, and we have a y plus. So then to solve for dy dx, we just subtract the y over and divide out by this. The idea is that over here with 2, where we use the repeated y box, every single term should always have a dy dx popping up because of the composition of y into something. You always end it with a times dy dx. So it enables us to factor out the dy dx out of this part, subtract that over and divide and solve. So we subtract the y over, and we divide by that. And this right here is what dy over dx is. Very useful to use boxing technique for implicit differentiation in finding out what the equation for dy dx is. Thanks for watching.